My name is Malan. Like Stefan, I wear two hats. One hat I wear at Arbor Networks, which is a commercial entity, and the other hat I wear as a researcher at the University of Michigan. What I want to talk to you a little bit about today is the observation and experiences we've had tracking denial of service attacks across regional ISP. In a lot of senses, this work complements the talk you just heard. So, whereas the previous talk looked at a global perspective of what denial of service activity looked like, this is a sort of snapshot of what happened within a specific network. Okay, so I just want to give you like a quick project overview of what we were trying to do and where we came from. We'll go over the collection methodology, a summary of denial of service statistics we measure within this network, and then summarize at the end. So to give you a project overview, this is work we call it the Lighthouse Project that we started at the University of Michigan in collaboration with Merit. This is work that was funded back in '98 by DARPA. The focus was really on looking at the network availability in a provider's network, focusing in specifically on denial of service attacks. I also like to thank, of course, Cisco and Intel, which also were very generous with equipment donations for this project. I need to acknowledge my collaborators on this as well. At the University of Michigan, we're Farnam, Jahanian, John Arnold, and Matthew Smart, and at Merit, Paul Howell, Russell Dwarshuis, Jeff Ogden, and John Poland. So quickly going to go over the collection methodology. So what we're trying to do in a nutshell was we were trying to measure within a single provider's network. We want to find out which routers were affected by denial of service attacks when they happened, what interfaces on those routers were. Examples of these attacks are, you've heard these words before many times: Freenode, TFN, Socklejack, Endstream, etc. So now I kind of go in a little bit more to the meat of the stats here. We're trying to answer a number of different questions basically while looking at this data. How many attacks were we seeing on the provider's network? How much of it was inbound attacks versus outbound attacks? Recognize that the ISP was mainly educational based, so there were a lot of non-firewall machines sitting around just ripe for compromise and launch pads for attack. We wanted to find out how long did the attacks last, how big are they, and also look at some of the target characteristics of the attacks as well. So look at the domains as well as the target autonomous systems. Finally, we wanted to break down and figure out what's the instance of source IP address spoofing. Was it mostly totally spoofed, or was it a subnet spoof? And finally, how much bandwidth was being wasted in the network as a result of this attack. So looking at whether the ISP was being synced or sourced to attacks. So for the attack types we're looking for in this data, you see that it's primarily overwhelmingly outbound attacks. So this again breaks down with correlation with the fact that these were educational institutions and for local launching pads, so to speak, for attacks. Let's see. Again, looking at the CDF of attack magnitude within this ISP, it corroborates nicely as well with the previous talk. I think a kind of neat thing to look at here is that you notice that both the SYN and the no flag floods take up a lot less space, say, than the ICMP and EDP-based floods, and that's what's really happening there. The no and the SYN flag floods are using really short packets basically to do the attack, so they take up a lot less bandwidth. But when the other guys, which are mostly bandwidth related. So looking at how much bandwidth was wasted there in the ISP. So you saw over the course of about 4 or 5 months there was about 234 gigabytes of SYN flood, 32 gigabytes of ACK, 13 gigabytes of null, about 200 EDP and 250 ICMP, which ran to about 720 gigabits. Whether or not this is big or not, we realized it was a fairly small ISP with not huge pipes to the rest of the internet. So if you left the sort of spigot running for the entire duration of the trial, you had about 1.3 kilobits per second, 1.3 megabits per second, sort of trickling outbound the whole time. So looking at now what in the ISP, what was being attacked by the people who were launching from the ISP as well as internal to the ISP. We saw that most of the attacks were actually in this data set against home users, either through DSL, dial-up, or cable modems. The majority having signatures from CAN tool sets, where the source spoofing, bandwidth, and periodicity are pretty much what you expect. But we did see, corroborating with the past talk, there was a small but significant percentage of sort of custom attacks that are on the rise. So looking at the domain space under attack, somewhat different. We don't see the Romania here. I guess that was not a great launching pad for Romanian attacks. But you see predominantly .NET, .com, and .edu were the main TLDs. There's about 58 TLDs that aren't on here because they only had 1 or 2 attacks. And you see that, based on the target, there's a fairly random distribution of the type of attack as well. So again, looking at target autonomous systems, I wasn't allowed to show the target AS numbers from this ISP because we didn't want to get in trouble. But the majority of these were really aimed at cable modem users. And at this AS, there's a tier 1 here that was getting a lot of UDP attacks. Porno sort of based AS here was getting a lot of ICMP. Transit with some UDP. This one was kind of a neat one. It was a foreign government, which is like a foreign government's Bureau of Investigations AS that was totally being basically SIM flooded all the time, and then a nice Midwest educational institution that was being SIM flooded. This is kind of one of the more interesting slides in the talk here. This is really looking again at how prevalent was full address spoofing versus subnet-based spoofing. And we saw that this broke down very clearly between whether the attacks were inbound versus outbound, or versus outbound. So for the outbound attacks, we saw that red is subnet-based spoofing. Green is where you're actually spoofing across the whole 32 bits, and blue is where it was kind of a simple attack where it was just a single machine during the flood, or a single IP address during the flood. That the outbound attacks were primarily subnet-based, so almost all of them were in fact. Whereas the inbound attacks have a somewhat larger proportion of the full 32-bit address space. So, whether or not this is a representative of the whole internet or not, it's certainly one data point that suggests that the magnitude of attacks out there are at least 2, maybe 3 times greater than Stefan's estimate for global attack magnitude. So some of the ongoing analysis we're doing right now, we've deployed this technology in a number of large hosting centers, enterprises, and backbone providers. We have noticed that there, as Stefan was saying in the last talk, there's an increasing number of attacks against the actual infrastructure itself. I removed the slide that will detail this from this talk by request, but we kind of avoid this somewhat. We see that there also is some significant differences lately in these sort of differences in severity of the attacks. And some of the things that we're looking at from a research perspective is we're looking at doing target service identification. So figuring out what services we're actually running, what targets that we measure the attacks on. And it's not much of a summary, but I just want to let you know we transferred the technology out of University of Michigan in Ann Arbor about middle of last year. And if you feel free to email me or check out the webpage if you'd like more information. Thank you.
Hey, Rob. Stefan. And I'm curious about the results that you saw about the breakdown of source address spoofing, because if you look at all of the tools from the Trino time frame onward, that means all of Stockwell Drought and TFN2K and so forth, this is all done automatically by the code as a function of ingress filtering. And so it doesn't surprise me, because what will happen is they'll first send a test to see if the full spoof 32-bit approach works. If it does not, if they're not able to pass through the filter, they will back off to a /24. Actually, some of them will back off on even finer grain prefixes. But so what I would expect here, why you see this breakdown, is because you have ingress filters at the edge. It tries to do a full 32, and then when in fact it cannot, it backs down to a /24, which has been the standard behavior for a year and a half.
Sure. So there's also a flag to a lot of these tools too, which is how do you want to do these spoofing? And the flag is really 2 states, one full or the other 8 bits on the end. So
do you have evidence which one is doing? What is going on if the
I don't.
Okay.
So clearly, one of the things we could read from this is that our ISP is actually doing a better job, or at least all its customers are doing a better job of ingress filtering. But it's impossible to really know which it was in this case.
Your data indicate that attacks on the infrastructure are increasing. Are you finding that the attacks on the infrastructure are more effective, or are they self-defeating in the sense that if they attack the infrastructure, then the very infrastructure carrying attack goes away, so the attack goes away, so the attack stops?
Yeah, we've done no quantitative analysis of what the impact of the target service really is for these attacks. So it's hard to know whether. And then give you anecdotal evidence. For example, there was an attack that was basically they had done some reconnaissance and they had done trace route through the network, and they were attacking every single router interface along the path basically, and so it disrupted a significant portion of the ISP's operations. So it was very effective in bringing down the service to the actual target itself, as opposed to not.
Thank you.